Hi guys, welcome to my first physics YouTube lesson. Please bear with me. Being my first lesson, this is probably going to be pretty low quality, so just follow along and try not to get too motion sick. Okay, so the first thing we're going to do is we're going to review the equation for observed frequency given the Doppler effect. F sub O is equal to F sub S multiplied by V over V plus or minus Vs. And this is the different cases you use. When the source is moving away, you use V plus Vs, and when the source is moving toward, V minus Vs. Right, so I assigned a couple of homework questions, but I'd like to take up one of the sample questions here. A car traveling at 100 kilometers per hour sounds its horn, which is 440 hertz, at a hiker on the road. Assuming the temperature of the air is 0 degrees Celsius, determine both the observed frequency as the car approaches and as the car moves away. So the first thing that we're going to calculate here is we're going to calculate the speed of sound in air. So we use the speed of sound in air equation. V is equal to 332 plus tau 0.59, tau being the temperature in degrees Celsius. So we sub that in and we find that the speed of sound in air is 332 meters per second. I notice here that the car is traveling at 100 kilometers per hour, but my speed of sound is in 332 meters per second. So what I'm going to need to do is I'm going to take one of these and convert it to these two similar units. And I've decided I'm going to take 100 kilometers per hour. And right there, those are my conversion factors, and I'm converting it to meters per second. So 100 kilometers per hour multiplied by 1 hour over 3,600 seconds times 1,000 meters over 1 kilometer will yield 27.8 meters per second. Okay, so I'm going to first find the observed frequency as the car approaches. So F sub O is equal to F sub S times V over V minus Vs. So the source frequency is 440 hertz. Then I multiply by the speed of sound in air divided by the speed of sound in air minus the speed of the source, which is 27.8 meters per second as we previously calculated. And look, I get an observed higher frequency. When it's moving away, I just, again, sub in the numbers, and as you can see, when it moves away, we hear a lower frequency. Flipping the page, we see the applications of the Doppler effect and the Doppler shift. In astronomy, astronomers examine the light coming from distant suns and galaxies. If the light wavelengths are lengthening, this is called a redshift. The reason why we call it a redshift is if the wavelengths are lengthening, that means the wavelengths are getting larger. As we can see right here, wavelengths are getting larger. And wavelengths getting longer, light wavelengths getting longer, means that they are shifting more to the red end of the visible light spectrum. And that's why it's called a redshift. And the astronomers can then determine the speed at which the star and galaxy is moving away from our solar system. If the light wavelengths are shortening, this is called a blue shift, and that makes sense because blue is at the other end of the visible light spectrum. This is called a blue shift, and the astronomers can determine the speed at which the star and galaxy is moving toward our solar system. Police radar, so police obviously have radar guns and they set up speed traps along the road, and they do the following. They emit a frequency that gets reflected by the oncoming car. Because the car is approaching, the frequency will be higher. So since the emitted frequency and the reflected frequency are similar, so again, the gun has an emitted frequency and the reflected frequency is going to be slightly higher, but they're similar, so they produce beats. The number of beats per second is then electronically calculated into the speed of the car. This technology can be modified for a stationary speed trap or for a patrolling police car. So you don't necessarily always have to be still. The police car can actually be moving and they can still use this technology. Okay, the next part of the lesson that we didn't really get to was supersonic air travel. So let's quickly define that the objects traveling at speeds below the speed of sound are said to be traveling at subsonic speeds. And objects traveling at speeds beyond the speed of sound are said to be traveling at supersonic speeds. And as you can see here, we see an aircraft that is breaking the sound barrier, which we'll talk about in a second. back to here where the Mach number. The Mach number is the ratio of the speed of an object to the speed of sound in air. And so we use this equation right here. Mach number is equal to v object over v sound. Taking a look at the sample problem, the speed of sound at sea level in 0 degrees Celsius is 332 meters per second, or 1,200 kilometers per hour. At an altitude of 10 kilometers, and there is a decimal there, you may not see it on your page, so I've just really kind of penciled it in there, making that 2 significant digits. The speed of sound is 1060 kilometers per hour. Determine the Mach number of an aircraft traveling at 1800 kilometers per hour. So we take the Mach number is equal to, and the speed of the object is 1800 kilometers per hour. We're obviously assuming that the aircraft is flying at an altitude of 10 kilometers and not at sea level. So 1800 kilometers per hour divided by 1060 kilometers per hour, which is the speed of sound right here at the 10 kilometers, and we get the Mach number of 1.7. So traveling faster than the speed of sound, meaning that it is traveling at supersonic speeds. Okay, breaking the sound barrier. So the above right picture, which is over here, right there, that's a picture of an aircraft breaking the sound barrier. A stationary object will produce wavefronts emanating from the center. As an object moves closer and closer to the speed of sound, the object catches up to the wavefronts. Recall that sound is the compression and rarefaction of air particles. So a wavefront will have a compressed air or high air pressure. Okay, so they have like the front, the wavefront will have compressed air. Okay. Once the air catches up to the speed of sound, there will be several compressed air wavefronts through which the aircraft must brake. If it wants to go faster than the speed of sound, it's going to have to brake through those compressed air wavefronts. Okay, and that compressed air. This is called the sound barrier. And if an aircraft is not properly designed to push through the sound barrier, it will be destroyed. Okay, so as we can see here, this right here is a stationary object, right? And these are the waves emanating from the stationary object. Okay. This is an aircraft traveling at subsonic speeds, and as we can see, as it travels along, there are the compressed wave fronts right here, but it has not passed through them yet. Right, as we can see, the front of the aircraft has not passed through those wave fronts, so it's traveling below the speed of sound. Here, it is traveling at supersonic speeds, and as we can see, the front of the aircraft has passed through the wave fronts right here. And so therefore, we have it traveling at supersonic speeds, and we have these spheres of wavefronts emanating from the aircraft. And they happen to be, as we can see, in C, the sphere of wavefronts are in phase, which produces constructive interference. As a result, you get a loud sound because of this constructive interference, and that's produced when the airplane breaks the sound barrier, called a sonic boom. Okay, and the sonic boom is then heard in what's called a noise cone that emanates from the source that has broken the sound barrier. So if you turn to page 271 in the text, you can actually see the noise cone that's produced from an object traveling faster than the speed of sound. Okay, and this is typically done. Aircraft typically break the speed of sound away from populated cities, usually over the ocean or in unpopulated areas. And the reason for that is the sonic boom can sometimes be so loud it can shatter windows or cause structural damage to buildings and whatnot. So the sound barrier is typically broken over large bodies of water, right? It even has an effect on the wilderness populations. If aircraft are breaking the sound barrier too frequently over a certain area, that will have a negative effect on the wildlife living in that area. Okay. There's homework here on page 270, numbers 3 to 5, and page 272, number 1 to 5. Another really little interesting fact that the book tells you as well is when somebody cracks a whip, that little snap that you hear is a mini sonic boom. Okay, and that's the tip of the whip traveling faster than the speed of sound at that portion, right? And that produces a small sonic boom that can be heard. Okay, so that's it for Chapter 7. So just get that work done and make sure that the notes are properly filled in.